Hello everyone, welcome to my heat transfer project presentation. So for this project I have developed an EASE code to analyze the performance of a heat exchanger. At first I will introduce the basic mechanism of a heat transfer, then I will introduce the plate fin heat exchanger. So a heat exchanger is a device to transfer heat from hot fluid to cold fluid across an impermeable wall. Fundamental of heat exchanger principle is to facilitate an efficient heat flow from hot fluid to cold fluid. This heat flow is a direct function of the temperature difference between the two fluids, the area where heat is transferred, and the properties of the fluid and the flow state. This relation was formulated by Newton's law of cooling, which we can easily express by this equation. Here we see that it depends on some parameters, uh, which is H, which is heat transfer coefficient, A is the heat transfer area, and T is the temperature difference. Heat exchangers are one of the vital components in diverse engineering plants and systems. So the design and construction of heat exchangers is often vital for the proper functioning of such systems. The main requirement for any heat exchanger is that it should be transfer the required amount of heat with a very high effectiveness. In order to increase the heat transfer in a basic heat exchanger mechanism, increasing the heat transfer area generally is the best engineering approach. The above requirements can easily be met if by using another type of heat exchanger. It's called plate. Is called a compact heat exchanger. So plate fin exchanger is a type of compact heat exchangers where the heat transfer surface area is enhanced by providing the extended metal surface interface between the two fluids and is called as the fins. So the main objective of the present work is to evaluate the performance parameters like overall heat transfer coefficient, effectiveness, and pressure drop of a control flow plate fin heat exchanger through hot testing under balanced flow condition. Here we see the test section, and it consists of a counter flow plate fin heat exchanger with offset strip fin geometry. The geometry of the offset strip fin surface is described by the following parameters like fin spacing, fin height, fin thickness, and fin strip length. So as a testing fluid, we are using air, and the air flow rate through the testing section was set using the control valve and the temperatures and the core pressure drop across the heat exchangers. The system was then allowed to run until the steady state is achieved. Once the steady state was achieved for a particular mass flow rate, the air flow rate and the temperature are accurately measured for estimating the rate of heat transfer and various performance parameters like effectiveness, number of transfer units, and heat transfer coefficient. In order to find the performance of present heat exchanger, a number of experiments are carried out at different mass flow rates and hot fluid temperature of 96 degrees Celsius are used under balanced flow condition. Now I will show the EASE code for our performance analysis. So this is the equation window for our EASE code. At first, what we do, we make a lookup tables where we put all the experimental values from our experiments. We have run 5 experiments. So this 6 column actually indicated the volumetric flow rate for our 5 experiments, the temperature of the cold fluid in inlet and outlet, the temperature of the hot fluid in inlet and outlet. Also, we assumed the number of transfer units for our calculations of the overall thermal conductance. In the equation window, we can easily see that we use the lookup table to gather all of our experimental data into the equations. Then we convert the volumetric flow rate into the mass flow rate, where we convert the P into Newton per meter square. We also use the outer temperature of the hot fluid. Then we have easily calculated the mass flow rate for our fluids. We also have the heat capacity of the cold fluids and the heat capacity of the hot fluids. Then we can uh, easily calculate the value of capacity rate ratio. If we see the heat capacity of hot and cold fluids, we see that the heat capacity of cold fluid is lower than the heat capacity of hot fluids, and it's our C minimum value. By using all of these values, we can easily calculate the hot effectiveness and the cold effectiveness for our fluids. We can also calculate the overall heat transfer conductance for our assumed number of transfer units. Then we have these parametric tables to show all of our calculated values. In these parametric tables, we have the mass flow rate in kg per second units. We also have the effectiveness for the cold fluids. We also have the effectiveness for the hot fluids. We have the overall thermal conductance. So we can easily plot all those values in some separate graphs. In these graphs, we can see the variation of effectiveness with mass flow rate. It is seen that effectiveness increases with mass flow rate. Experimental hot effectiveness first increase, then becomes almost constant for certain mass flow rates. Plot 2 described the cold effectiveness with mass flow rate. Plot 3 actually is the comparison of the effectiveness of hot and the effectiveness of cold fluids. In this plot, we can see that hot and cold effectiveness increases with increasing mass flow rate and try to approach each other, and there is an optimum point at which the effectiveness, the gap between the hot effectiveness and the cold effectiveness is minimum, and then again increases. Also, after the optimum point, the cold effectiveness decreases with mass flow rate. This is because a heat exchanger is designed for a particular mass flow rate and inlet temperatures at which it gives maximum effectiveness, after which its performance becomes deteriorate. In the plot 4, we try to demonstrate the variation of overall thermal conductance versus mass flow rate, from where we can see that the hot when the hot inlet temperature is 96 degrees Celsius, the overall thermal conductance is also increased with mass flow rate. It is due to the fact that with increasing mass flow rate, the Reynolds number increases, and as a result, Colburn factor is also increased, which is directly proportional to heat transfer coefficient. So overall thermal conductance is also increased. In this way, we can easily calculate or evaluate the performance of heat exchangers if we have some experimental results or data. Then we can easily compare our performance data by plotting some graphs, and we can easily demonstrate these graphs to see the overall performance of a heat exchanger. So thank you. That's all.